this video is going to be a brief introduction to the PID controller, which is a type of feedback controller that takes in proportion, integral, and derivative calculation to reduce error in a system as much as possible. So when I refer to error, I'm going to define this as an error function with time being an input, and we're going to set this equal to r of t minus s of t, where r of t equals your set point and s of t being your current position, and this of course being your error right here. So really what this means, when I say set point is essentially what your end goal is, so where you want to end up being. So if you have, let's say, like a robot that wants to drive forward 5 meters, your set point will be 5 meters. So it's whatever you want your whatever you're trying to do, what you want your end goal to be. So your error would be whatever your end goal is minus your current position. So this is going to be very important throughout this video because I'm going to be using this definition of error to basically break down the different parts of the PID controller and how the basic math and essentially how the PID controller can actually reduce error in a system. So what we're going to be going over first is the proportional controller. So the proportional controller is defined as U of t, which we're going to call our output. So our output is going to be proportional to some constant multiplied by our error. So basically whatever our output is going to be, it's going to be exactly proportional to our error. So we're going to basically explore what this really means through like a basic situation. So what I'm going to do is, sorry, excuse my really bad drawing skills. I'm going to draw a car here, and this car, he's traveling at a steady pace of 25 miles per hour. Now, what this is going to look like is if we draw our velocity versus time graph. So this is our velocity, this is our time. We're going to be kind of steady like this at whatever this is. This is going to be 25 miles per hour. So what in reality, so let me draw this out. This is our speed limit. Our speed limit is 35 miles per hour, and we want to be driving exactly what the speed limit is. So obviously 35 miles per hour is larger than 25. So our desired set point, 35 miles per hour, is going to be above this 25. So this is our set point. So if you remember from before, our error, E of t, is just going to be whatever your set point is minus your current position. So our set point is 35 miles per hour, and our current position is 25 miles per hour. So we have an error. So if I draw this kind of like a line here, we have an error of 10 because 35 minus 25 is 10. So to fully explore like how this controller really works, I'm going to draw basically what our output is going to be in this situation. So if we imagine the gas pedal, so this is like the guy's leg. Oh, whoops. The guy's leg, and he's pressing down on this gas pedal at some angle. It really doesn't matter. It's just some angle such that he's traveling at a steady pace of 25 miles per hour. So this is going to be some angle here. So we're going to define this theta as being 0 degrees equals not pressing gas. So we're going to say that our 0 theta means that we're not pressing down on the accelerator at all. So if we then draw our theta versus time graph, I actually want to extend this a little bit. Theta versus time. So we're going to have, this is time. So if we're traveling at 25 miles per hour, that means our foot is at some like position. So our theta is going to be at some constant angle for now. So when we apply this proportional controller, if we draw a graph of our error, this is E, not Euler's number, but error versus time. So our error up until when we apply the proportional controller is going to be constant because we're at 25 miles per hour and we want to be at 35. So it's just going to be a constant 10. So when we apply this proportional controller, what happens is we're going to basically get a little bit of a kick in. So we're going to press down on the accelerator a little bit. So then this angle is going to be at a new lower position. So our angle increases, which means that we're pressing down on the accelerator, which will cause our velocity to increase because we're pressing down on the accelerator. So what happens then, if our velocity is increasing, that's going to cause our error to decrease because we're approaching whatever our set point is. So this error will decrease. Now here's the thing. It's called a proportional controller because the output is proportional to the error. So if our error is decreasing, that means our output will also decrease. So in this situation, our output is our theta. So how much we're changing our theta. So what's going to happen is as our error is decreasing, that's going to decrease how much we're going to press down on the pedal. So then this velocity will increase even more. It's going to increase. And then our error will also decrease. And then what's going to happen is as we apply this proportional controller, our theta is going to keep on increasing, and it's going to eventually like kind of taper off into like a steady position, which is the angle necessary to drive at 35 miles per hour. So then our error is going to decrease to 0. It's going to taper off until it reaches 0. And same with our velocity. Our velocity is going to eventually reach whatever our set point is. So that's basically the basics of a proportional controller. And then what we're next going to look at is what happens when we combine a proportional and derivative controller. So when we look at the rate of change of error. So now that we've explored the proportional controller, we're going to be looking at the proportional derivative controller and to what context it applies in. So what I have here is sort of the same like context as we had before, except a little bit modified. So now we have a car here that's stopped at a traffic light, and we have another traffic light up here ahead. So our goal is basically when we see this green light, we want to drive forward and up until like we see this red light, and in which we like stop at some point over here. So you can think of our set point as being the distance from this car, so like right here, all the way to right here. So this would be our set point. So I'll just say, I don't know, D as like distance. So let's see what would happen if we were to apply just a proportional controller. So if I have right here, so I'll draw the graph of our angle theta versus time, and I'll draw the graph of our velocity versus time, and I'll draw the graph of our error versus time. So what this is going to look like is when we're stopped here, our error is going to be very large. It's going to be whatever that distance is. And then when we apply our proportional controller, we know of course that we're going to push down on this. We're going to change our angle pretty fast. Let's try that again. We're going to change our angle pretty fast, and that's going to cause our velocity to increase. And then what's going to happen is our angle is going to taper off to some whatever this is. And same with our velocity. And eventually our error is going to decrease to 0. So everything looks good, right? Well, this will not work because what's going to happen is, wait, let me draw this a bit better. So it's going to look something more like this. So this is not good because we're tapering off to some constant angle, and we're still traveling at a constant velocity. So what's going to happen is our car here is going to fly right past this stoplight because we're still driving at some velocity when we reach our set point here. So what's going to happen is our error is going to go negative, and we're going to basically oscillate between two values over and over again, which will kind of look like us flying past the stoplight and then stopping, going back in reverse and flying past it again, and kind of be in like this oscillating motion, which will never actually eliminate this error. It's always just going to be oscillating. So this is one of the times where we want to apply a proportional derivative controller. So when we use a proportional derivative controller, we are going to define our output. So u of t, let me just write this real quick. So u of t as being equal to kp, so some constant, times our error. So basically our proportional term. And then we're going to add in a second term, which is going to be kd, so again another constant, times our rate of change of error with respect to time. So when we add in the second term, what we're going to be doing is we're going to be taking into account how our error is changing over time. So whether it's increasing, decreasing, or just not changing at all. So what I'm going to do, I'm just going to redraw our graphs real quick with a few extra changes. So this graph is going to be the rate of change of our angle position over time. So how we're changing our pedal position over time, so as we're approaching the second stoplight. And then second graph is going to be our velocity versus time. Third graph is going to be our error versus time. And then we're going to add in a fourth graph, which is going to be our change in error versus time. And let me just extend the axis a bit. We'll see why in a bit. Okay, so when we are going to apply this controller, so a proportional derivative controller, what's going to happen is, so initially our error is going to be pretty large, and our proportional controller is going to want to decrease this error a lot. So what's going to happen is that we're going to push down on the pedal and reach our highest change in pedal position at the start. So we're going to initially push down on the pedal pretty hard. And what that's going to do is our error is going to decrease over time because of that. It's going to start to decrease. So the key part is this term right here. So our rate of change of error. So what's going to happen is that over time, as our error is decreasing, our rate of change of error is going to be sort of like this. So our error is decreasing, meaning that our rate of change of error is going to be negative, since our error is, of course, decreasing. The slope is negative over this region. So the key part is that, so our proportional controller is going to look something like this. We're going to reach our highest position and then go back down to 0 until we stop changing our pedal position. So the key part is that when this derivative term starts to become larger in magnitude than the proportional term, what's going to happen is that our output is going to start to become negative, meaning that as we're approaching the second stoplight, we're starting to slow down the car, which is exactly what we want. We don't want to fly past this and just completely miss it and get like a traffic ticket or something like that. So what's going to happen with our velocity versus time graph, we're going to initially speed up, and then we're going to reach our highest point, and then as we approach the second stoplight, we're going to start to slow down until our velocity approaches 0. So what we're going to do is our car is going to speed up and drive past the first stoplight and then successfully stop at our second stoplight. And so this is essentially how we can use the proportional derivative controller. And next we're going to look at why we would use a proportional integral derivative controller. Okay, so now to show how the integral term comes into play, we're going to set up this new situation where we have two cars, where this is car 1 and this is car 2, and these two cars are traveling at the same velocity, with this car right here, car 1, being behind car 2. So the point of this situation is we want car 1 to, we're assuming that this car is in a different lane than car 2. We want car 1 to catch up to car 2 and then start to drive alongside car 2. So if we were to use our traditional proportional derivative controller, as we've seen before, remember that from the previous situation with the two stoplights, basically the car would speed up and then slow down as it approached the second stoplight. So in this situation, that's not what we want, because what's going to happen is our car is going to speed up to some speed, and then it's going to reach some position, starting to get closer and closer to the second car. But what's going to happen is that since the derivative term acts as a damping force, since our error is decreasing, it's going to cause our output to become negative, meaning we are letting off of the pedal. And what that's going to cause us to do is it's going to cause our car to slow down to being at some position right here. So when we use a proportional derivative controller, what happens is we eliminate some of the error, but we don't completely eliminate it. We're not accomplishing what we want to accomplish. We're not driving alongside the second car. So you might think, what if we just use a proportional controller? Wouldn't that work? Well, the problem with that is that with a proportional controller, what's going to happen is if we're changing the change in pedal position, so how much we're pushing down, like how much we're changing, how much we're pushing down on the pedal, what's going to happen is our car position is going to go from being right here to speeding up past this car. So we're going to start driving faster than the car. And so what happens is that since our position is going to be past the second car, our error becomes negative, meaning our output becomes negative. So what's going to happen is we're going to slow down the car a little bit. And what's going to happen is what we've seen before, where a proportional controller, in a lot of cases, ends up in this oscillating motion, where we never really eliminate the error. So when we have something like this, where this car is trailing behind the second car and is like removing some of the error but not eliminating it entirely, this is called steady state error. So if we have, let's say we have some other situation, so this is not related to this, but let's say we have a graph of our velocity versus time, and we have a set point velocity of up here, whatever this velocity is. So what a steady state error would look like is if our velocity reaches a point where our error decreases, but then our velocity settles at a point that's lower than our set point. So we have eliminated some of the error, but it's not completely eliminated. We haven't reached the speed that we originally wanted to reach. So this is an example of steady state error, where we have this kind of, as the name suggests, a steady error as time goes on. So the solution to this is to use a proportional integral derivative controller, where we add the integral term. And so how this integral term will affect our overall output, it's going to basically sum up our past error. So if I just erase this graph real quick. So if we add this integral term to our controller, our output will become u of t equals kp times e of t, so our proportional controller, plus kd times our rate of change of error, so our derivative term, and then our third term is going to be, we add ki times the integral from 0 to t of e of tau d tau. So really, the math behind it isn't really too important to understand how this controller works, but essentially what this is going to do, if we have a graph of error, so error versus time, what this is going to do, this term right here, if we have this steady error, what it's going to do is it's going to sum up all this past error. So all these little chunks underneath this error kind of, I don't want to say curve, but basically error curve, it's going to add up all this past error. So let's see what this will do for this situation. So I'm going to redraw our graphs. So this is going to be change of angle versus time. This one's going to be our velocity versus time. This will be our, we're actually going to add our angle versus time, or change, or our pedal position versus time, and then we're going to have our derivative, oh shoot, that looks like a P, derivative versus time, and then finally we're going to have our fourth graph here, which is our integral versus time. Oh, sorry, and one more graph. We have right here our error versus time. So when we're trailing behind this second car right here, what's going to happen is our error is going to be sort of constant. So before we apply this controller. So when we add this integral term, what this is going to do is it's going to accumulate a bunch of error until it reaches this sort of constant, until it reaches like a constant value. So what this is going to do is it's going to essentially give the controller a little bit of a kick and eliminate this first part of the error. So something like this. It's going to eliminate a little bit of error. And then what's going to happen is after we've accumulated all of this past error, this will, like the proportional derivative controller will continue as normal. So our change in angle position is going to, it's going to look something like this. It's going to change to some other position and then slow back down to 0 again. And then our derivative will go from, let me just draw this entire graph of error. It's going to look something like that. Our derivative will be 0 until our error changes, where then it's going to become negative, reach its most negative point, and then go back down to 0. And then our theta, so whatever our pedal position is, if we're driving at a constant speed, it's going to be at some like position that we're pressing down on. And then what's going to happen is it's going to increase, meaning that we're pushing down harder to speed up. And over time, it's going to decrease back down to the same value again, because we're wanting to drive alongside car 2, which is traveling at the same speed as us. So we want to speed up and then eventually travel at the same speed as car 2. So what this is going to look like for velocity is we're going to be traveling it's going to be similar to our theta versus time. So we're going to be driving at some velocity, speed up a little bit. Oh crap. Speed up to some value and then slow back down until we're matching this speed once again. So this PID controller will eventually get our car to where we want to be and successfully complete the task and have our first car drive alongside the second car. Alright, so finally, to wrap things up, I'm going to show you guys like a quick diagram of the entire process to show you how everything comes together to become one cohesive feedback controller. So before we get into that, I'm just going to quickly review some stuff. So remember that U of t is our output, E of t is our error, and then S of t and R of t are our position and set point respectively, and then our Y of t will be our physical output, and I'll show you what that means in a bit. So if we remember from the start of the video, I defined error, so our E of t, as being E of t equals R of t, which is our set point. So set point minus current position. I'll show you how that comes into play in a bit. So when we use the PID controller, we're essentially going to input an R of t, so a set point. We're telling the controller, I want to reach this position, and I want you to figure out what the optimal output over time is to accomplish this task, to reach that set point. So we put this into something. This is going to be called, and also this is going to be positive. We're going to put this into something called a comparator. And this comparator is going to, exactly how it sounds, it's going to compare our current position, S of t, with our set point, R of t. And with this comparator, it's going to calculate whatever our error is. So it's going to be our R of t minus S of t. And then this comparator is then going to take this error, so right here, this error, E of t, and put it into our PID controller. So this is going to split this error up into 3 parts. So up here is going to be Kp times E of t. Down here is going to be Kd times our rate of change of error. Oh, sorry, I guess this should be integral since we're doing PID. So Ki times integral from 0 to t of E of tau d tau. So summing up our past error. And then the rate of change of our error. So Kd times the rate of change of our error. And by the way, if I haven't mentioned this before, Kp, Ki, and Kd are all arbitrary constants that I'm using. And in this situation, I'm assuming that these PID constants have all been tuned. And I'll explain in a future video how you would actually tune these constants. But for now, we're going to assume that these are completely tuned and are functional for this controller. So then what it's going to do is, after putting this error into the PID controller and calculating our output, is going to take this and again sum it up. Sum up all of these components. Oh, that's not a sigma. What am I doing? It's going to sum up everything and produce it as our controller output. So our U of t. So a controller output you can think of as being like a motor voltage. So we're setting a motor to run at X percent voltage. So this controller output is telling the controller, oh, I want the motor to be running at this amount of voltage, and in order to like accomplish what you want to do. So then this will take it into the plant. So the plant is where you are applying your output. So in this case, if it were motor voltage, we are going to take this motor voltage and apply it to the or give it to the motor controller, so that the motor controller can use that to do whatever you want to do. So basically, the plant is where you are performing your process. So for example, like a robot, you would take this output and give it to the robot in order to perform whatever task you're trying to accomplish. And then what's going to happen is this is going to output a Y of t, which is your physical output. So when I talk about physical output, I mean like an actual movement of the robot. If you want the robot to drive forward 4 meters, a Y of t, your physical output, is the robot physically driving. It's not giving a motor voltage command to the robot. So U of t is essentially a calculation of what you need to do in order to accomplish your task, and Y of t is your actual output, how your robot is moving over time. And then what's going to happen is this is going to loop back around to the very start, hence the name feedback controller. Oh, that's an error. Yeah, so this is going to loop back to the start, and it's going to loop through this over and over again until our error is completely eliminated. And that's essentially the basics of a PID controller. So I hope this video helped in some way, and I wish you guys luck in your future robotics endeavors.